In this video, we're going to look at 4 problems involving energy and are relevant for our upcoming tests. Here first, a little review of the loop. Imagine we have a loop-the-loop where there's some cart that's going to be coming down the loop-the-loop from some height h. And let's imagine now in an actual lab, in reality, we have 2 photo gates that are going to measure the velocity of the cart. One at the very bottom, we call that velocity v sub b, which was 5 meters per second, measured by our photo gate, and then pretend we have a photo gate also at the top of the loop where it measures the speed to be 4 meters per second. We can call those the energies at the bottom and the top respectively. And of course those total mechanical energies, signified by the capital E, are the sum still of all of the gravitational potential energy, UG, plus all of the kinetic energy, K. The question here is, if we're able to measure the cart's velocity at the top and the bottom of the loop, and say that we know the radius of the loop to be 0.1 meters, and the mass of the cart to be 0.5 kilograms, how much mechanical energy is lost? So we know in reality there's going to be some non-conservative forces such as friction and air resistance that are going to make some of the mechanical energy change into another form, like heat loss due to friction, or pressure waves from sound when you hear the thing clanking through the loop. So if we want to find out how much that change in mechanical energy has been made, we can look at the total amount of mechanical energy at each position. Look at how much total mechanical energy there is at the bottom. That's just all kinetic. If we use the very bottom like we did in class, the very bottom of the track as the 0 line, then I have from these values 6.25 joules at the energy at the bottom. At the top, now, I have a total mechanical energy of 5 joules. It's the sum of the kinetic energy plus the potential energy up at the top. So this difference here is the total energy at the top, that's our final position, minus the total energy at the bottom, and that difference is minus 1.25 joules, or that tells us we've lost or have 1.25 joules less mechanical energy than we started with. The principle of the conservation of mechanical energy implies that we must have a constant amount of mechanical energy all of the time. But this assumes that there is no work being done by non-conservative forces. So, since we do have some lost mechanical energy here, we must conclude that there was some work done by non-conservative forces such as friction or air resistance, and this would be the case if we were able to do this in the lab, put a couple photo gates there, and see how much energy is lost. These could be, we say lost, but we should say it's left the system. That's what's meant by there's mechanical energy that's lost. Or it's basically just unaccounted for. We still believe in the conservation of energy, we just have to go looking for other places that this energy may have gone to. So that means heating up part of the track maybe from the friction. The sound that we hear, those are pressure waves moving through the air, and a wave is a transfer of energy, so there goes some of the energy that way. Or if we have something like radiation or light being produced, then that requires energy coming from somewhere, and if it comes from the total mechanical energy of the system, then once it leaves, the system is going to have a lower mechanical energy after that light or radiation leaves. Another problem we'll look at is the example of slides or curved ramps, and we saw this with the example of 4 ramps that I demonstrated in class. Those black metal ramps, they each had a slightly different curve to them. A couple of them were straight, had the same slope, and a couple of them had different slopes that were curved. This is also similar to the Hot Wheels labs we've done. So 2 common questions to look at are, 1, how do the speeds compare to the 2 identical carts if they get to the bottom? And they should have the same speed at the bottom if they have the same height. So the orange bar there shows the same height that they're released from. Regardless of the shape or the path, the conservative force of gravity does the same amount of work, and therefore they both, since they start with the same amount of gravitational potential energy, they therefore have the same total mechanical energy at the bottom, which means all of that energy must be turned into kinetic. So their speeds are going to be the same if those energies must be the same at the bottom. Which cart reaches the bottom of the ramp first depends on the shape of the track, and also its length. But the shape we saw, since the ones in class are about the same, they're about the same length, and they were both the same height, the different shapes show us a different angle, and the acceleration is a function of that angle. So if I have a steeper angle, then I'm going to have a greater acceleration down the ramp. Of course, if I make a very low-angled ramp, it'll be very long. If I have a very low acceleration, it'll take a long time for the cart to reach the bottom. All of these 2 and some of the ones in class were curved, which means that the acceleration is changing as the cart goes down the ramp. And so as the angle becomes less steep, then the acceleration is going to become lower. That angle goes down and the acceleration goes down. The value of that acceleration in particular is going to be g times the sine of the angle. You can see that from a free body diagram. The other thing they might ask regarding this is then, okay, so the one with the steeper track, the red one's going to reach the bottom first. They're both going to have the same speed. Which one's going to have the more kinetic energy? Well, kinetic energy is made up of two values, the mass and the velocity. So if they have the same velocity, then the only way they're going to have a different kinetic energy is if they have different masses. So they could have the same velocity at the bottom of the track. They should in these examples. But if you have a different mass, say one of the carts is twice the mass than the other, then that cart with more mass is going to have more kinetic energy at the bottom of the ramp. Here's a problem a little more involved. We had the opportunity to kind of look at the velocity after a change in energy with the Hot Wheels tracks if you let the car fly off the end of your table. And in this one, this question, which is from Dan Fullerton's example problems that we can look at is the same sets that I've posted from before. This one asks if there's a dart of mass m accelerated horizontally through a tube of length L, situated at a height h above the ground, by a constant force F. Upon exiting the tube, the dart travels a horizontal distance delta x before striking the ground as depicted in the diagram. So this is just a horizontal projectile. Instead of having a dart accelerated through a dart gun tube with length L, you could have a sort of ramp that starts over here on the left, like a Hot Wheels track, and curves down, and then you have a cart or a ball that is accelerated down the ramp by gravity and flies off the end horizontally and has some initial velocity v when it leaves the end of the table or wherever it's flying off of. It'll still be a horizontal projectile, same situation. In this question, we're asked to look at a couple things in terms of literal equations, which is good to practice with. Part A asks to develop an expression for the velocity of the dart v as it leaves the tube in terms of delta x. So delta x is down here, that's the range of this projectile now. H, its height above the ground, and any fundamental constant. So g is the example of the fundamental constant that we'll use in this one. I can just solve this range equation, which is here coming from a kinematic equation, that delta x, the distance that the object's going to travel horizontally, which I've drawn in red, is equal to the product of the velocity horizontally, which does not change in a projectile. Horizontal velocity stays constant because it's the conditions of free fall. There are only the force of gravity is acting on it. There's no air resistance. So that range delta x is the product of the velocity in the x direction, vx, times the amount of time it takes for the object to fall, which I've written as t fall in blue to distinguish from the red in the horizontal. We got blue in the vertical. So if I solve that for v, then I've done the first step of developing an expression for the velocity. I've solved an isolated v, the velocity, which equals delta x over t fall. Delta x is something that's given in this problem. We're saying find it in terms of delta x, h, and any constant. So I've got delta x, I can leave that alone. I just need to solve for t fall. And t fall is solved over here on the left under the tube, right there. So if I have some, start with a kinematic equation, delta y, I can find my t as square root of twice the height over g. That's the amount of time it's going to take any object to fall in free fall if it has an initial velocity in the y direction of 0. So there's my expression down at the bottom then. Here, for the velocity of the dart as it leaves the dart gun or dart can. Part B asks to derive an expression for the kinetic energy of the dart as it leaves the tube in terms of m, the dart's mass, delta x, h, and any fundamental constants. So there's my k equals 1/2 mv squared, and this v is going to be the velocity of the dart as it leaves the tube, and where m is the mass of the dart. And I just found that v in part A, so I'm just substituting in my expression for the velocity. That goes in over here, and that value is squared. And so I simplify it, and I get mg delta x squared over 4h. Just got to get rid of my fraction in the denominator of my fraction. That reciprocal gives me g upstairs and 2h downstairs, and 2h downstairs times 1/2 is 1 over 4h. That's why that's downstairs. So mg delta x squared over 4h is the value for the kinetic energy of that dart as it's leaving the tube. This is an important value to have because it's experimentally, if I'm doing something like, say I do have the dart gun, or up here at the very top left, some ramp that starts with some potential energy way up here at the top where the cart is, all that's converted into kinetic. It still has some potential left over because it's about to be projected horizontally and fall a further distance, but I have some new energy here at E0, And if I can solve for the velocity in terms of these other values, then I can determine what the velocity should be if I can measure the range and the height of, say, the table. And I can track that back to my change in kinetic energy, because I know in part B I can solve for my kinetic energy, and then I can compare that again to the total energy at the very beginning of the whole process, which perhaps could be all gravitational potential if I'm talking about maybe a cart being released from rest from a curved ramp that I've kind of annotated on top of the diagram. Or I could relate that back to maybe the potential energy inside this tube of length L. Maybe there's some potential chemical energy, such as in a gunpowder, that's going to accelerate a dart. Or compressed air, maybe, that's going to accelerate a dart. So here's a good example of continuing to use our literal equations and previous things we've learned, like projectile motion, in order to relate the values to kinetic energy and velocity. Last question is looking at ramps, work up a ramp. Now there are a couple questions on the first problem set I gave you that are basically exactly the same as this, but I forgot to do one more. This is a work up a ramp on an incline. Assume there's a 50 kilogram container and it's going to be dragged up the incline, and this incline has an angle alpha and a height h. The coefficients of static and kinetic friction are known, and I'm writing out values of known things right there. If the container is to move up the incline with a constant speed of 4 meters per second, A, find what must the applied force be. So that could be the tension in a wire or a string that you're using to pull it up, or it could be you just pulling it up, whatever. How much power in part B is required for that applied force to do this work? So first things first, we'll draw a free body diagram. See where my green block on the ramp represents the object, the cart, the block, what did I call it, a 50 kilogram container. And I have 4 forces that I've diagrammed. Before I write in what they are, I'm going to show where my axes are. There's blue, positive y, x in red is the positive x axis. I've shown which forces I have, that applied force up the ramp. I have F sub k, kinetic friction. I know it's going to be Fk because it said the container is moving at a constant speed of 4 meters per second. So I'm talking about kinetic friction. In the opposite direction of the object's motion, I have force normal in blue and the positive y-axis perpendicular to the contact surface. And Fg, which equals mg, is always straight down. I drew that in purple because it's not on any of my x or y axes that I've drawn, meaning I'm going to have to resolve it or break it down into its component parts. I also indicate where the angle alpha is. Here are the components of my gravitational force vector. I have mg cosine alpha. That's the component that's adjacent to my angle alpha, and that is right opposed to my normal force. It's in the opposite direction of the normal force. Then I also have mg sine alpha, which is the component of gravitational force down the ramp or parallel to the ramp. Part A is looking at what is Fa going to be if you're going to get it to move at a constant speed up the ramp. I invoke the second law, sigma F equals ma, and I'm talking just about the x direction. I have a positive applied force up the ramp minus the kinetic friction minus the component of gravitation down the plane. I'm fighting against gravity and friction to move this block up the plane at a constant speed. Its acceleration is 0, so I have 0 in for acceleration. I know it's 0 because I said it's going to be at a constant speed. I solve for Fa, which is Fk plus mg sine alpha, and now I need to do a little more to show what Fk is equal to. By considering my y dimension and invoking the second law again, we see that normal force must be equal to mg cosine alpha, something we've seen before. Otherwise, the container is accelerating in the y direction off the plane. Then I can continue to solve for the applied force. Here I've done it numerically. You can see what the final value is. We also have to recall again that our friction is Fk is equal to mu k times the normal force. So I'm able to get an actual value for that since I have the kinetic coefficient and I also have the value for the normal force. Continuing over with B, we're looking at the power required for this to happen, and I wasn't given any time, but I was given some dimensions of the incline and also the speed with which the container is going up it. So we write out a couple relevant equations. One, we remember that the work, or in this case the work done by just my applied force we're looking at, is equal to that force times the cosine of the angle between the force and the direction of motion of the object times the magnitude of the displacement, called s. This is measured in joules or Newton meters. My power is the work divided by the change in time, or basically how quickly that work is being done. Now this is watts or joules per second, or newtons times meters over seconds. Let's look at the work first. I have the work by the applied force, which we already solved for, which is 336.6 newtons, and it's going to be the cosine of 0. To convince ourselves, look over here back at the diagram. That's 0 degrees because we're looking at the angle between the applied force, or the force we're talking about when we're looking at the work, the angle between that force and the direction of motion. So there's my direction of motion in purple, and my applied force is the large vector arrow FA. They're in the same direction. That angle theta is how far, see my smaller red vector that I've drawn in there, that would be a red vector that has some different direction, that's not in the same direction of motion, and in that case I would have a non-zero angle to look at. If it's drawn all the way in the opposite direction, like the work done by friction, it would have an angle of 180 degrees, the cosine of which is -1, and so that would indicate to me that my friction is doing negative work, or work in the opposite direction of the object's motion. Last part is going to be the distance that this thing is being moved, and that's 3 meters divided by the sine of 30, because I know the height, and I'm looking at where the applied force is being applied, up the incline. So I need to find that hypotenuse, which is 3 meters, the opposite side, divided by the sine of 30. That gets me 6 meters for the length of the hypotenuse. The cosine of 0 degrees is 1. And so the total work done by the applied force is about 2,020 joules, or 2,020 newton meters. Boxed it in green. Now we go over to look at the power. Work divided by time. I know the work, but I don't know the time. I do know the length, and I do know the speed. So because I know a distance and a speed, I can find the time, which is 1.5 seconds, or 3/2 seconds. Substituting that in, I can find the power required for the applied force. So this would be like if this applied force were part of like the tension in a string, and that tension line were over the edge of the incline around a pulley and attached to a winch, a machine that would wrap it up, then the power required by that machine to do this lifting would be equivalent to 1346.4 watts. That's how much power that machine would need. And the work, of course, would be about 2,020 joules or newton meters. One last thing, look back at these units real quick up there. I just drew the red arrow. Newtons times meters per second, or newton meters per second, is another way of talking about power. And if you think about those units, those newtons are the same as force times velocity. And what happens when I multiply the force needed by the applied force by the velocity of 4 meters per second, ta-da, I get the work in watts again. So a little shortcut there, instead of having to determine the amount of time, just do force times velocity. That's it for those 4 problems relevant for our FRQs on Monday. One last thing I'll add. Anything else? I'm going to go back. Nope, I think we're good. That's it.